All right, so we just left off by looking at a one population mean test where sigma, the population standard deviation, was known. And what I want us to get to in this video is what if our population standard deviation is not known? And in that case, remember, when sigma is unknown, then we're going to estimate it with the sample standard deviation S. Okay, and so it actually ends up being that the t-test is a much more commonly used test for a population mean because usually we don't know the population standard deviation. What happens is summarized in the handout, so you can read the information there on your own. But basically, when you don't know the population standard deviation, we can't use the Z formula anymore, and we end up replacing sigma with S, the sample standard deviation. But what that does is it creates a little bit more variability in our estimate. And so instead of having a standard normal distribution, we have a distribution that's still symmetric, still centered about 0, but ends up with more variability, so more spread. And this is called student's t-distribution. And so what happens when we replace sigma with S, you'll notice that the test statistic looks very similar to it when it did for Z. The difference is sigma is replaced with S, and instead of a Z distribution, I now have a T distribution. Okay. And so again, I'll let you read through the rest of this handout on your own. You have access to it. A couple of important pieces of information is that as our sample size increases, our sample standard deviation S becomes a better estimate of the true population standard deviation sigma. And as that happens, the t-distribution starts to decrease in spread until it looks more and more like the t-distribution. So actually, for infinitely large sample sizes, that t-distribution becomes identical to the z-distribution. So what happens, because that t-distribution decreases in spread as the sample size increases, we end up with a different t-distribution for every possible sample size. And so each t-distribution is going to be defined by an additional piece of information, which is its degrees of freedom. And for the test for one population mean, the degrees of freedom is just going to be the sample size minus 1. Okay. So we're going to go ahead and move on to an example. And in this example, it says the ankle brachial index, ABI, compares the blood pressure of a patient's arm to the blood pressure of the patient's leg. The ABI can be an indicator of different diseases, including arterial diseases. A healthy or normal ABI is 0.9 or greater. And in a study, researchers obtained the ABI of 187 women with peripheral arterial disease. And we're told the results were a mean ABI of 0.64, standard deviation of 0.15, and at the 5% significance level, do the data provide sufficient evidence to conclude that women with peripheral arterial disease have an unhealthy ABI? So this is a hypothesis test for one population mean. We know that the healthy ABI would be 0.9 or greater. So we're going to look at this sample of women and see if the average is 0.9 or if it's less than 0.9. Because we don't know the population standard deviation, in fact, we're told we take a sample and from that sample find a mean and a standard deviation. Then we need to go ahead and use a t-test.